value, and it can do that as well. Simple imputer has several strategies. Sometimes you may replace it by the mean, if you by the median, if you think that there are outliers that may affect the average. For example, if you have an income column, it's always a good idea to replace it with the median rather than the mean, because there will be outliers that may affect the average. Okay, so many different strategies. We are going to use a simple strategy of filling in nan values with the average value in that column. So how do we do it? We import simple imputer, and then we create a simple imputer object with some parameters, in this case with just a strategy. But you can check what other parameters it supports simply by typing simple imputer and a question mark before that. So here you can see that this is all the help available for simple imputer. You will also see some examples. Missing value, you can also specify what the missing value looks like. In this case, it's np.nan, that's automatic. You can specify what strategy you want to use and so on. Okay, so we create the imputer. Fine, now we've created an imputer object. So first, before we perform any imputation, let's just check how many missing values we have in each numeric column so that we can verify later that those were filled. So if we just do on the raw df, which is the entire data, check, get the numeric columns and check is any, which is replace each value in the data frame with a true or false, whether or not it is null, and then take the sum. So all of this business is just to count the number of missing values in each column. You can see that min temp, max temp have a low number of missing values. Evaporation, sunshine have a fairly high number. Evaporation, it seems like almost half of the data is missing. On the other hand, we have for some of these other things, there is a reasonable fraction of missing values. Okay. And here, this is the entire data set, but we could also check these individually for the training, validation, and test sets. For example, here is the check for just train inputs, checking missing values just for the training data. And you will see a similar pattern or similar fraction in the validation and test set as well. Okay. So with that out of the way, the first step in imputation is to fit the imputer to the data, which means that we give it the data that we want to fill, and it's going to look through the columns. It's going to look through all the columns. So it's going to look through the min temp, max temp, rainfall column in the data frame raw df numeric calls, which is just the numeric columns chosen from the raw data frame. So this, and it's going to go through each column, and for each column, it is going to figure out the statistic that you've asked it to figure out, the imputing statistic. In this case, we're using the mean or the average. So it's going to compute the mean for min temp, mean for max temp, mean for rainfall, mean for evaporation, and so on. Okay. So let's call imputer.fit. So it's not yet changed any of the data. We've not filled anything in. We have simply calculated the statistics. So if you now check imputer.statistics underscore. So for the first row or for the first column that we gave it, and remember these columns are simply the numeric columns that we have picked. So for the min temp column, it has figured out that the average is 12. For the max temp column, the average is 23. For the rainfall, the average is 2.5, evaporation average is 5.4, etc. We have asked it to compute averages. It has computed averages. Now, once these averages have been computed, then they need to be filled into the test set, into the validation set, and into the training set. So here's how we do it. We say imputer.transform. Let's take it step by step. So let's look at train inputs.numeric calls. Okay. So this is just from my training data, which is the 60% data, just the numeric columns I've picked out in a data frame. And obviously there are a lot of nans here. Then we call imputer. The imputer already knows the averages for all of these columns, min temp, max temp, rainfall, etc. And we call imputer.transform. And it's going to fill all the nans with averages. And now that becomes a numpy array. So you can't really see here, but if you look at this numpy array, you will see that it does not contain any nans. So it has looked at all the nans and it has replaced those nans with those average values. Now it's not showing you a data frame because imputer just outputs a numpy array. But what we can do is we can take this output, this numpy array, and we can put it back into the data frame as the new values for the numeric columns, right? So we are overwriting the numeric columns now in the original train inputs data frame with the imputed data, which means with the nans replaced with the averages. Okay, and we're doing that for validation data. We are transforming the val inputs numeric calls and overwriting that into val inputs numeric calls and so on. Okay, so all of this business, imputer.transform and then storing the data back, all of this is simply to get to the point where if I now check train inputs numeric calls, you will see that now there are no nan values. Now those nan values have been replaced with the average value, which I guess in this case you can probably tell 5.47 is probably the average value for evaporation, 7.6 is probably the average value for sunshine, but only the nans have been replaced, not all the values. Okay. And now you can check for each of the training, validation and test sets that there are no missing values at all. Okay. Now that's the average imputation technique, but you can try other imputation techniques like median, or sometimes you can also use other columns to impute data. So there are several techniques, just check them out. There's an entire module in scikit-learn that does this. Okay. Now we've dealt with missing values. Another good practice is to scale features to a small range of values. Right now, if you check the numeric features or the numeric columns of data, you will see that they have a fairly wide range. For example, min temperature goes from -8 to 33. On the other hand, wind speed goes from 6 to 135. I think this is min and this is max. Let's see. Yeah, pressure at 3 p.m. Okay, this seems to go all the way up to 1039 and the minimum seems to be 977. Now, what happens is when you put all these numbers into a machine learning algorithm, and you apply weights to them and then you compute a loss function, ultimately the loss is a single number, right? The cross entropy or root mean square loss, etc. The loss is a single number, and we say that higher the loss, worse the model. But what happens is if a certain feature has a very high range of values, maybe like rainfall takes values that are in the thousands, but minimum and maximum temperature take values that are in less than 10. And maybe there's a certain column where the values are 0.00 point something, which are basically in the decimals. So what happens is that the values which have a very high magnitude tend to dominate the loss, because it's ultimately all these numbers getting multiplied and added together. So the values that have a high magnitude, the features that have a high range, tend to dominate the loss, but features that have lower absolute values and features that have lower range of values tend to not show up in the loss as much. So what happens is that if what dominates the loss also dominates the optimization process. So that means the values which have these high numbers their weights are going to change a lot, but the values which have low numbers or smaller ranges, their weights are not going to change that much during optimization. So just to give everybody a level playing field, just because we measure rainfall in a certain unit where it gets large values, but we measure temperature in a certain unit where it gets lower values. So just to level the playing field for all the features, what we like to do is we should scale all the features into a same range of values. So we're going to scale the features, we're going to scale all the numeric features into the range of values 0 to 1. And sometimes this is also -1 to 1. Either one is fine, it depends on the circumstances, but 0 to 1 is fine for classification problems. And the way you do this is using a min-max scaler. So from sklearn.preprocessing, this is again another module, and we are in fact what we're doing right now is called preprocessing. So from sklearn.preprocessing, import min-max scaler, and then you create a min-max scaler, and then you can give it some options. Like you can give it, you can check here, it supports like a feature range, it supports whether it should create a copy of the data, etc., etc. But the objective of the min-max scaler is to identify for each column what is the minimum and what is the maximum, and then scale the values in the column so that they all lie in the range 0 to 1. So it's a two-step process, just like the imputer. First, we fit the scaler to the data. So we compute the range of values for each numeric column. So we say scaler.fit raw df numeric column. So what's happening here is it's going to look at each column from raw df, the entire data frame, min temperature, max temperature, rainfall, evaporation, etc. It's going to look at each column and it's going to find the minimum and maximum of each column when we run scaler.fit. So now we have, if we check the minimum, we can say that the data minimum you can see that for these columns, for the numeric columns, which are min temp, max